Math 2414, differential equations, video 5. Another example of a separable differential equation. The first two examples we've done so far were pretty easy to separate because they were just fractions. And so they were the functions of x and functions of y were virtually already separated just on the same side of the equation. But sometimes it's not that transparent. For example, we're going to solve dy dx equals x squared y squared plus x squared plus y squared plus 1. At first glance, this might not look like a separable differential equation because the right side is not a product or quotient of a function of x and a function of y. Here's a product of x's and y's plus an x term plus a y term plus a constant. Doesn't look like a product or quotient of anything. However, being Calculus 2 students, factoring should not be an issue for you. This guy is factorable, and more specifically, is factorable by grouping. I am going to go through the motions of factoring this by grouping under the assumption that you know how to do it already, and if you don't, then search my channel for a video about factoring by grouping. Alright, so anyway, we'll split it in two groups and factor the GCF out of the first group. We have x squared on the first group, leaving a y squared plus 1. And on the second group, we would factor out the greatest common factor also, except it doesn't seem there is one, but that's because the greatest common factor is the number 1, and more specifically positive 1, leaving y squared plus 1. And since each group has a common factor of y squared plus 1, we can factor that out as a common factor, leaving behind an x squared and a plus 1 as the other factor. And so, yes, this differential equation is separable because the right side can be written as a product of a function of x and a function of y. And now we separate by getting all the y terms on the left and all the x terms on the right. If we multiply both sides by dx, we would get x squared plus 1 dx on the right. But what about what's going to happen on the left? Well, since the function of y is multiplied on the right, to move it to the left, we would have to divide both sides, or equivalently multiply by its reciprocal, and get 1 over y squared plus 1. And then we integrate. For those in my class who are going to do this homework, I am okay if you do the integration immediately upon the separation. In other words, you don't need to write this without the integral signs, and then again with the integral signs. Alright, so let's integrate this. The right side is trivial. The right side is just going to be 1/3 x cubed plus x plus some constant. The left side not trivial, except it is. Because at this stage of the game, you should recognize that that's the derivative of arctangent. And so the integral of this will be arctangent of y. No need for a plus constant over there because we can move it to the right side, merge it with the other constant into a single constant. Can we solve this for y? Absolutely. Take the tangent of both sides and get y equals the tangent of 1/3 x cubed plus x plus a constant. So that really wasn't that bad. I think the hardest part was actually getting the functions separated at the beginning, but actually separating them on either side of the equal sign was okay. And the integration wasn't that bad unless you forgot this, which I hope you don't, because you're in Calculus 2 and you should know that by now. Do we have an initial condition? No. Could I pull up Desmos and show you the graphs? Of course I could. Am I going to stop the video to do that? Not really. Do I want to know what they look like? Of course I do. So I'm over here on this computer, just getting ready to type that in there. And if it's noteworthy, I will grab my camera and come over here and show you what it looks like. 1/3 x cubed. Whoa! Great, really moving. Plus, and that probably means I'm going to show you x plus a constant. Add a slider. And let's animate that slider. Wow, this is crazy. You're like, show me. Okay. You know what? I'm not gonna. Because in the previous video, I showed you in Desmos how to type an equation, add a slider, and animate it. The only reason that I went whoa is because you should know that the graph of tangent is a bunch of little curves trapped between vertical asymptotes. But the vertical asymptotes occur at values where the argument is odd multiples of pi over 2. So when you put a constant here and put it equal to, well, it can equal a lot of different things, but those asymptotes aren't equally spaced. So, oh shoot, I'll just show you. All right, so there's the equation and there's the slider. Let's take the slider down to 0 for a second. But if you'll notice, I'm going to animate it. I'm going to animate the slider, and this is just like, kind of looks like a fluid flow or something. I am going to go in and slow the slider down. You can do that. Because this has so many branches that it's all choppy when it's animating. And that's a little bit smoother. So yeah, that's pretty interesting, all of its solutions. And again, if I stop the slider at any moment, that graph represents the solution to the differential equation. It's the solution where the constant is equal to that. Let's do one more thing. Let's make the, let's go -10 to 10. And this time we'll control the step size. Let's go in steps of 1/100th. And then let's see what that does. We'll speed it up just a little bit. And we get this, what I think is a pretty beautiful illustration of these curves, just kind of like flowing through a river or something. Now, I've admitted in previous videos that I am not a physicist or an engineer, so I really don't know if fluid flow has anything to do with the tangent function, but it's just pretty.